All right, this is AP Calculus lecture, the second lecture from section 3.9. I'll call that 3.9b. And this lecture has two parts. The first part is approximating the value of a function using the tangent line equation. So we're going to use what we learned in the first lecture from 3.9, how the tangent line can give you a good approximation or estimate of the actual value of a function when that function is difficult to find the actual value. So our example is going to be take the or approximate the square root of 4.1. Okay, so it's easy to get the square root of 4. You know that's 2. Well, what's the square root of 4.1? Can we use calculus to give ourselves a good estimate of that? All right, so step 1 is to form an equation. Okay, so what equation makes sense for the square root of something? Well, it would be that would be f of x is equal to the square root of x. So if I were trying to approximate the cube root of something, it would be the cube root of x, right? Or if I were trying to approximate the square of something, it would be x squared, okay? So you just form an equation that makes sense with what you're trying to approximate. So step 2 is we want to pick an easy point nearby. Okay, so what would be the easy point? Well, we know that the square root of 4 is equal to 2. Well, 4 is near 4.1, so let's pick that. All right, if I were trying to find the cube root of, let's say, 28, I'd pick right the cube root of 27 because that's equal to 3. So, you want to pick an easy point nearby. So what that's saying is that we have f of 4 is equal to 2. So that's our x value. Our x value is 4, and our y value is 2. So we're looking at the point when we form our tangent line equation of 4, 2. All right, our next step is find the slope of the tangent line. Okay. Well, we know how to do that. To get a slope of a tangent line, we're going to take the derivative. So let's rewrite this as f of x is equal to x to the 1/2. So f prime of x is equal to 1/2 x to the minus 1/2. All right, I'm going to rewrite that as 1 over 2 times the square root of x. So our slope is going to be f prime of 4, our x value, right? We're plugging in the x value. So that's 1 over 2 times the square root of 4, which is 1/4. All right, so our tangent line slope is 1/4. Now I got to erase a lot of this and go to our next step, so pause the video if you'd like, all right, to get caught up. Okay, so we've got the slope of the tangent line. And we have a point 4, 2. So step 4 is get the tangent line equation. All right, so that's going to be y minus y1, all right, that's just 2, is equal to 1/4 times x minus 4. I'm going to go ahead and solve for y here. That's going to make it easy when I plug in my point nearby. So we have y is equal to 2 plus, when I distribute the 1/4, that'd be 1/4 x minus 1. So that simplifies to y is equal to 1 plus 1/4 x. And then the final step is substitute the new value to get estimate. Okay, so we're going to substitute that new value here into x. All right. So we're trying to find the square root of 4.1, right? So we're going to substitute that into y is equal to 1 plus 1/4, using that tangent line equation, times 4.1. All right, put that in your calculator, you get an answer of 2.025. That's your estimate. If you stick the square root of 4.1 into your calculator, go ahead and pause the video and try that real quick. Take the square root of 4.1. So from your calculator, you'll get 2.0248. That's really close. You can always, with these problems, you can check your answer. You should be getting an answer that's really close to what your calculator says it is. All right, so within 2 1/1000ths, you can't really complain. That's a very good estimate there. So we'd even get a better estimate if we got closer to 4. If we were to take the square root of 4.01, our answer would almost match what the calculator says. I mean, to many decimal places over. So since we're getting a little farther away from 4, our estimate is off just a little, but not bad at all. All right, the next topic in 3.9b is called error propagation. So I'm going to erase this if you would like to pause. Okay, so differentials, so that is a concept I introduced in the last lecture, can be used to estimate propagated error. When measurement error is known. Okay, so if we have that dy dx is equal to f prime of x, we know that dy is equal to, multiply both sides by dx, f prime of x dx. So dy is what we call propagated error. And dx is our measurement error. You'll be given measurement error. Let me tell you what I mean by that. So let's say we have a ruler. Hopefully you can see this. So we've got this ruler. And you know it's not a perfect ruler. It's been made in a factory. These markings are on the ruler. But the factory can give you a good idea of how much error is in each measurement. So let's say that this ruler is accurate to plus or minus 0.01 millimeters, okay? They will guarantee the measurement up to 1/100th of a millimeter. So that's your measurement error. But anytime you are then measuring something that is, say, really long, or you're measuring an area, so you have a length times a width, or a volume, you've maybe got a length times width times height. You are getting not just a measurement error of 0.01, you are multiplying that error many, many times over. And that multiplication of error is called propagated error. You can think of that as maybe the total error, or the accumulated error. Okay? So let me work a couple of example problems for you. So in your textbook, if you'll look at example 24 on page 226, it gives us a cube. So I'm just going to draw a sample cube here. All right. So one thing we know about a cube is that the length of every side is the same. So that's x, that's x, that's x. They're all x. So if we, in this particular example, it says that our measurement error is 0.03 inches. Okay, so we know that measurement error. We want to figure out the propagated error for measuring a cube, both the volume of the cube and in part B, the surface area of the cube. Okay, so first you have to get an equation for volume. We know that volume is equal to x cubed, since we gave length times width times height. There. All right, we need to take a derivative. dv dx is equal to 3x squared. So dv is equal to 3x squared dx. So dv is our propagated error, dx is measurement error. So then we can plug our numbers in. dv is equal to 3. All right, the side of each cube is 12 inches. Got to square that. And then the measurement error is 0.03 inches. So that's our dx value. All right, multiply that out and you'll get 12.96 inches cubed. But that's the way the book will say it, but I would rather you give me a little more information in your answer. So we know the volume is going to be 12 cubed, right? X cubed. So that's 1,728 inches cubed. So the way that you would give us that measurement is that the volume of this cube is 1,728 cubic inches, plus or minus this error, 12.96 inches cubed. That's the way I would like you to tell me your answer. That gives you more context, okay? This is this cube has a lot of volume, 1,728 cubic inches. So the error, plus or minus 12.96, is not a very large percentage of the 1,728, is it? So just 12.96 cubic inches might sound like a lot, but in comparison to the entire volume, it's not too bad. So that's why I think you need to give your answer. This is more of an engineering way of communicating your answer, not just a mathematical way. All right, let's look at example B. And this time we're looking for surface area. All right, example B, we need an equation for surface area. So with a cube, you have six sides, and each side has an area of x squared. So we would have 6x squared. So our derivative of surface area with respect to x is going to be 12x. So DSA would be 12x dx. So let's plug the numbers in. DSA is going to be 12. The side, x, is 12 inches. And then that's 0.03 inches for our measurement error. All right, so 12 times 12 times 0.03 would give you 4.32, and that's going to be inches squared for your unit. All right, so the surface area is 6 times 12 squared, which is 864 inches squared. But it's going to be plus or minus the error, because the error could go up. You could get a reading as bad as 868 or a reading as bad as 860, right? So, or close to that. So plus or minus 4.32 inches squared. So that does it for today's lesson on 3.9b, and I will talk to you next lecture.